Hi, I'm Christian Clark. I'm from the math department in Würzburg University. So Würzburg is in Germany. So here's a map of Germany. You see Würzburg is pretty much in the center, not far from Frankfurt, a beautiful old town. So once Corona is over, you may want to consider to visit. So I'm going to talk, I have joined, this is work with people I work with. So there's Katrin Helmuth, who's a PhD student here in Würzburg. There's Rui Yulai from Minnesota, especially in inverse problems. Chin Lee from Madison. There's Marlies Unna, Stock and Würzburg, and there's Min Tam from Shanghai Jiao University, the same place that Jin is at. So I'm going to give you a little bit of the context of this topic I'm going to talk about. So we begin really from the beginning. So when you model phenomena in nature, you take a atomic view. So you look at interacting particle systems, see it's on a very small time and spatial scale, and that's the microscopic modeling. And then, but if you go to like the bigger scale, you take the red box is not at the right scale. It's just supposed to show you how you, from all the particles, you take density distributions. So here's one shown in a particularization. T is shown. It's you get evolution equations for the kinetic equation, and there's the mesoscopic description. And if you go to the time scale Whelan and spatial scale, these become fluid equations, and that's the mesoscopic description. And so these equations, Euler and Navier-Stokes, of course, are famous. So we're going to, of course, focus on kinetic equations and their relationship to fluids. So you need, when you go from one to another, so here you have again the microscopic description, so n interacting particle systems described in Newton equation, just as I said before. When you let the particles go to infinity, particular limit, at least formally, you can derive the kinetic equations, and then when the collisions of particles very small goes to zero, the relaxation limit arrive formally, at least, at the Euler-Stokes or other limits, other macroscopic equations. And so you have rescale time space to go from one to the other. There's the Euler limit going from macroscopic to macroscopic, and there's a reducive limit depending on what phenomena you're interested in. The first gives transport, the other more as a diffusive phenomenon. So we're going to focus on this, the kinetic to fluid in diffusive limit. So let me give you an example. So here you have a kinetic equation, a neutron triad equation, where you need transport on the left-hand side, and then a particular action term on the right-hand side. This actually already interested in scaling. You can think of L equals 1 now. But if it's an epsilon and you let this epsilon go to limit equals 0, when it arrives at a macroscopic fusion equation, is notice that the F is something you can physically measure because it depends on, among other things, on the velocity. So in the macroscopic equation, you take average overall V, sorry. And that's what this diffusion equation looks like. Another thing, notice that aspects, interaction current, the kinetic equations, they show up in macroscopic fusion equations. So they're closely related. And that's one of the relationships to the things we're going to talk about in this lecture. So the PDE model at the mesoscopic level with initial data and boundary data, ideally we'd like to prove well-posedness of the solution, right? Well, say well-posedness of this equation. And if you give the correspondingly at the macroscopic level with the appropriate data, you would also like to show its uniqueness and use dependence on data for that. For that equation, actually, you all know how to do that if sigma is constant. And then if you have an object f epsilon and object rho, then you need to try to prove that in the appropriate alien you get this you prove the convergence in the right of this. So this is the idea. But rigorous proofs of such limits are really difficult, and so let me give you an example of something that so far, of course, nobody's been able to do. Namely, how do you reach from the oil limit in the oil limit to the compressible oil equations? Well, I'll tell you one thing, that obstacle here. So it is for 2D compressible oil, you see them here. First equation, conservation of mass, then conservation of momentum. Wellsness is enormously difficult, but it's not been achieved so far. And so what is one issues that you have in this equation? That's one thing we're working on. So consider an initial problem in 2. So down here you have the x1 and x axis, those are 2. And this is time, and on the left of the x1 axis you have a constant state, and on the right constant state. And in this picture actually 2 jumps come out. Only one will come out, but you see that it's 2 directions. This is a 1-dimensional problem, right? But it's now that in 2 space dimensions. And so here I give another example. I now no longer draw this one axis. So you think of this as a planar shock, cutting a constant state on the left, a constant state on the right. This is standard to the 1D problem, with also a solution to the 2D problem. But it's possible to show that in addition to the standard solution, there are many, many additional solutions. There, give them the name Y solution. So let's look. So this is the standard solution. So I've chosen my initial special here. And this is 2D down here, right? I'm just not drawing the other axis, where it's data which could give rise to a shock, but it's possible to prove that there exist additional solutions. They all are bounded by shock. That's the right thing. It's not known where inside. So that's in this paper in Simon Markfeld, Rational Mechanics. But it can be known that solutions are entropy solutions. And so it's not just the special data that lead to these many entropy solutions, but we have a paper where we describe the big set of initial data that gives rise to things. So you see an obstacle well posed to the Euler equations. So this is still open. Hence, if you know, this is one of the obstacles of this limit. Boltzmann tool. There are other additional obstacles, of course. But it's not bad. So the particular kinetic equation, which one could show well closeness. So I'll give you an example here. Something we work on. So consider a multi-species kinetic model. Okay, so you see here the first species given here, F described density distribution F1, the second species by F2, and this gives the interaction term of F1 and F1, and F1 and F2. Could you not off the microphone? And so this is the example for 2 species, but they're conduit for n. And so we do if you describe the interaction on the right-hand side by BG approximation, you need to now specify these Maxwellians. Here are the Maxwellians. They look as usual, except you have to specify all these red microscopic temperatures, velocities, and so on. Okay. And this paper has shown that one can determine these coefficients such that you have the concentration properties, momentum, energy, H therm hold. And So you have a good model, and actually one can show that's shown in this paper that this model is well-posed. So this joint work, among other Mali's. So there's an example of well-posed for kinetic model. So now next, let's use uncertainties. So in my example here, I'm back to the equation shown you before. Can transport, and suppose you're measuring coefficient with some uncertainties. So you represent that by a stochastic variable. So it's in stochastic. Now, of course, also it's on Z. And also the initial or boundary may be uncertain. That's another thing that happened. And if you go to the macroscopic equation, diffusivity coefficient, right? If you maybe some way you can measure it, but you measure some uncertainty, so you describe that. So it makes sense to look at things with certainties, and also the initial and boundary data can be uncertain. And so once you have your kinetic equation like that, how to solve that numerically? Well, one approach would be this generalized polynomial chaos method. So how does that work? Well, you take a set of orthonormal base functions for the space of random functions, expand f in a series with these basis functions. You truncate series and you substitute that in the stochastic system. This way you obtain a deterministic system for the first coefficients. So that's still a large thing involved, but you're back to deterministic equations. And so if you ideally one would show how accurate such a method is, right? And so one way to go about this is you check the roundedness and the decay in time of the derivatives. And so this is called hypocoercivity. So that's one topic that one looks at in this context. So for example, take a single species BGK equation, where now the collision frequency has a stochastic variable. And you attempt to prove K in time for F and for derivatives. So for the linear K equation, the F has been shown in Chin Li and Li1, this paper over here. And what we did is generalize this result, show decay fall in all derivatives in Z, using a Lyapunov technique by Achleit and Arnold. So what you do is you write F up from your BGK equation as a Maxwellian plus a deviation. So then you get the equation for the deviation, right? It depends on Z. And in this manuscript paper, we're able to show that actually we can get hypercoercivity, so the estimates for each L. So you can also do numerics for certainties in the context. So let me give you an example there. So here's the Scholes equation. This is an equation of finance, and I'm going to switch it on you. So you notice that in the beginning, it does look a little bit like a heat equation, right? Well, it has this S squared still. And so the way people in finance use this, yes, they use this. You can think of it as one also, turn time around, and I guess you change the sign, is that they first need to determine the coefficient, try to determine from a date on the market, and then they have this equation. So again, it makes sense to look at this efficient a stochastic coefficient, this utility coefficient, stochastic coefficient. Now, when you, in practice, you notice that in functional application, you notice that the solution coefficient depends on on finite number of stochastic variables. So the data is represented much better this way. That's the point. So now, when you use the stochastic approach, just showed you very, very costly, right? You can define stochastic approach for this object, and following a lead by you in the paper, we proved the computational efficiency of this bifidelity approach, using this bifidelity approach. And this is in this submitted paper with Hennenfent. And, well, I'm not going to explain the paper, but it looks good. So it actually compares market data with what you get, and it looks good. And so now back to the kinetic problem. So the forward problem, so what does this mean? So you give the initial kernel and you see the effect on solution. Okay, so that's the problem. That's what I've been discussing up to now. But there are situations where the parameter collision kernel has to be, you have to find it for the solution. So it's not something you can measure. You can only measure the solution and then try to find it from it. Okay. So the question is, given the solution or given part of the solution, the kinetic problem finds coefficient. Okay, and so this is the inverse problem for the kinetic equations. So let me illustrate. So here's the radiative transfer equation. So you see top guy in the kinetic equation in the radiant density, and the right-hand side is a physically reasonable way to write the induction term. And it's coupled, the temperature shows up in this right-hand side, and it's coupled to this equation. So the collision, the kernel describing the screen of photons is given, the absorption coefficient is given, the so-called emission coefficient is given a picture here. So the radiation density goes into this ball, right? Things get absorbed, but also things get emitted and things get scattered. Okay, that's the story. So now look at this. So what is the forward problem? So you want to find the radiation intensity, the temperature inside the ball. Then you would need a boundary, of course, given the kernel, the emission, and the absorption coefficient. Okay, so that's the natural forward problem. Is the inverse problem? Well, suppose you know what the emission coefficient is, so you want to infer that from the solution. So the kernel is given, the absorption coefficient is given, the temperature is given on boundary, and then you have some part of the boundary where the U is in, and you can measure U on the outgo part. So this is the problem. So U is given, this part of the boundary. You can measure, and so it's given on this part of the boundary. The absorption, the scattering is given. The question is, you infer what the sigma is. So this is an example of an inverse problem for a kinetic equation. So here's a result that with Yu Ray and Chin Lee. So we the stationary case of this problem. We set the scattering equals 0. And so now here's the problem that I described, right? This is, we want to infer sigma. And so actually it can be shown that this emission coefficient exists unique and depends continuously on data. And let me now show you the context of this root. Because remember I said you can relate a kinetic problem to its problem. Well, to do that, the limit to the macroscopic equation is kinetic problem I just gave, the stationary problem, leads to the elliptic problem. Okay, and this elliptic problem is similar to the Calderon problem and still posed. So I'll show you. Here's you have, remember before was the heat equation, so there was a UT here. Well, it's stationary now, so now it's the static equation. So here's this, it's now called activity in the microscopic, called it before this conductivity. And the question is, try to recover the sigma from much of the solution of some income part and go out part. And this is ill-posed. So notice, I've given you a kinetic inverse problem well posed, and I'm giving you as epsilon equals 0. It leads, this example, it leads to a macroscopic inverse problem that is ill-posed. Okay. Now, what do people do? Because this is questions like these are really important in technology. So what they do is solve this by a so-called Tikhonov regularization numeric. So whatever that is. And so we suggest solve this by approximating the inverse problem, the kinetic equation. Remember, the kinetic equation solution hopefully is not so far away from the macroscopic equation. For the kinetic equation, you can solve the problem. So maybe I can use that approximation to the problem of the macroscopic equation. So this word, instead of Tikhonov regulation, we use a kinetic regulation. This is the idea. So let me illustrate this for chemotaxis. So that. So here you have bacteria that move. So either they run in a straight line, or they stop and they turn and they move on. So you see them running, they turn, and then run again. So here's a photo of things. So they actually look like that. Isn't that amazing? And so they run, so on. Here's another nice picture. Bacteria, yeast bacteria move in the direction of a chemical reactant. Here I've taken the chemical reactant away. You see it just moves like that. And the chemical reactant is introduced. There's an overall movement towards chemical reactant. So, excuse me. So believe me, this is a model that describes the phenomenon. That's taken from the paper and so the kinetic equation, and like we saw before in the radiation transfer, the right side is equal to another equation. Okay, and so that's the chemotaxis equation. So already I've introduced this parabolic scaling here. And you can look at the limit of this mesoscopic model to the microscopic model, and you obtain the Siegel model. And so here you see your heat equation part, and it's built like that. Okay. So in the paper, they proved actually a solution to the chemotaxis. This is the forward problem. Converges to the solution of the macroscopic Keller-Siegel. Okay, so the solution's forward problem, one converges to another. It's this F epsilon going to rho, F epsilon going to part. This works. And now, in a solution, suppose a situation where inverse problem, where the kinetic equation is well opposed. So I assume that. Say this to the inverse part of the macroscopic equation, the color is ill-posed, then if the question is, does the inverse problem, well, how does this work, right? Because how do you get well-posed converge to an ill-posed problem? So this, okay, difficult. So the way forward now is to move a stochastic version of these equations, right? Because we want to make progress with this question mark. And so we move stochastic version of these equations. Because in practice, only noise data is available. And so it tends to use probabilistic setting. There are other reasons this thing actually has. There's a stochastic part. You can refine the model a little bit with this chemical attraction, also using probabilistic aspects and so on. So this makes sense. And so the way to look at the inverse problem is an Bayesian setting. And so we get the solution of the inverse problem, both for the kinetic and the macroscopic setting, in this Bayesian way. In that way, we try to find convergence of one to the other in an that's suitable. So this I think this is possible to do. So there's work in progress. Katrin Helmut, Shinli, and Min prove convergence in the Bayesian setting in appropriate norm. But I'll report on that in the next thing. But let me finish with what I'm trying to explain here. So clearly in modeling by PDEs, certain parameters are not known exactly. So certainty quantification was a time that you assume that these unstable or not accurately known parameters were stochastic functions, and then you solve the forward problem. So one could try to determine these modeling parameters by solving an inverse problem. Of course, that's pretty hard, but that would make sense. You do this experiment with this unknown problem, measuring data and try to infer that what it is. It seems natural that this question leads to look at the inverse problem in the Bayesian. So in future work, we plan to devise actually efficient algorithms to solve these inverse problems, and this way may possibly give a credible alternative to this ticket regularization. So with that, I want to end. So thank you for your attention.
Hi, Christian. I have a question about the last topic about the Bayesian inversion.
Yes.
Well, for elliptic problem, there's a very nice well-posed theorem. If you for the inverse problem, I'm wondering. I mean, have you already you have some similar result for like linear transport?
So where? So maybe I'm not aware of this. For the problems.
For the Bayesian inference theorem for inverse problem of elliptic problem, there's a very nice well-posed theory. So I'm just curious whether, I mean, you already have something like that for the linear transport equation? Because you are talking about this Bayesian inverse problem for linear transport. So I'm just curious, do we get something similar to what Andrew Stewart did for the elliptic problem? This is a well-posed. What do you mean? Usually, yes. Inverse problem is not well-posed, but if you just want to infer the probability distribution, then it is well-posed, right? So there's a nice elliptic theory for this. But right. I'm wondering whether that can be extended to the linear transport case.
I don't know the answer right now. But, when you say linear transport, you mean this kinetic?
Yeah. Kinetic, because it's not clear. It's close to diffusion equations, not really diffusion, but it's close to that.
Right. But I have to admit that it's these results of Stewart that were partially inspirational to try this. I think because of the right-hand side, which is not linear, it's slightly more difficult here.
Yeah. So you haven't got results like that yet. Okay?
No, not really in our case. No.
Okay. Thank you.